Vivek's presentation is cited a novel approach to measure adhesion between particles and to predict the powder flowability. A little bit background about Vivek. Vivek joined the Wolfson Centre for bulk solids handling technology in 2017, and he is pursuing a PhD mentored by Professor Michael Bradley at the University of Greenwich. His present research mainly focuses on solving flow-related problems of bulk solids handling industries and investigating the factors influencing the powder flow properties from a small quantity of particle to the particles at the bulk level. He completed his Master's of Engineering degree in Thermal Engineering in 2017 in India. His master thesis focuses on studying the flow properties of different powders. He received his bachelor degree on engineering and mechanical engineering in 2015. He has been working closely with many food and pharmaceutical industries, including Horlicks, Nectar Life Sciences, Sun Pharma, and other bulk solid handling industries in India and across the UK. So thank you, Vivek, and all over to you.
Good morning, everyone. My name is Vivek, and today we are going to talk about a novel approach to measure the adhesion between the particles and to predict the powder flowability. So in order to talk about this work, most of this work has been incorporated in the VFL Toolkit, which is one of the project funded by EPSRC. So moving on to the next slide. So basically, what is powder flowability? So before that, let me first talk about what are powders. So you can find a lot of definitions of powders, but generally a powder is a dry bulk solid composed of many fine particles which may freely flow or which may not flow. Like in case of castor sugar and icing sugar, it really depends upon the process and the conditions. For example, if we have castor sugar and we apply the consolidation stress, it may flow. Whereas if that same amount of consolidation stress is applied onto the icing sugar, it will form a lump. So therefore, it is the powders are dependent upon the characterization as well as the process in which they are going through. Generally, we have classified powder flowability into different regimes. However, we are looking for more definitive terms in terms of numbers to classify powder flowability. So talking about the flow problems. So basically, the flow problems, basically, if you talk about the blends or the formulation, so the blends can be generally prepared using different processes within the flexibility provided by readily reconfigurable set of configuration. So blends can be prepared with different ways like using direct compression or post granulation or pre-compaction. However, there can be two scenarios where there can be problems in blends, either if the powder is too or the formulation is too cohesive. So there can be different reasons for that. And the consequence can be that there can be difficulty in obtaining regular flow. If there is no regular flow, so obviously the production time will affect. And there can be a difficulty in roller compaction as well. And the second concern can be if the powder is too free flowing. So if the powder is generally free flowing, it may cause a problem of segregation, which may give rise to different problems such as content uniformity, as well as variable compaction. Since the audience is more focused on food and pharma both, so I think the cost of the failed batch in terms of pharmaceutical industry is a lot. So therefore, it is very much necessary to predict or to get the flowability behavior at an early stage of formulation. In terms of talking about food industries, still we need to save the powder, the amount of powder at an early stage. So I think there can be different way in which we can solve the problem, and I will be discussing one of the novel approach to predict the powder flowability. So talking about the flow stoppages, generally there is a flow stoppage called arching, where the powder sticks at the outlet of the hopper. Generally, if the powder is too cohesive, you can get a problem of arching. Whereas other flow issue is rat holing, where the powder sticks at the walls of the hopper. So these are two general flow issues generally faced in terms of formulation or even in terms of single substrate powders. So talking about why powder flowability is important, in industries, there is a general practice that in order to resolve these two flow issues, which I discussed in my two previous slides, people usually hammer down their hoppers, which is really a safety concern. So therefore, it is very much necessary that powder flowability should be studied and should be known in a proper way. We have got different indicators, manufacturability indicators, from where flowability can be really studied and can be really investigated. However, we still have got a best indicator for powder flowability, which is called flow function, which allows prediction of either what equipment is needed for a given powder, or whether, suppose you have got an existing equipment in your industry, so it can tell whether a powder will be able to flow or not. Obviously, it also tells powder flowability is important if you wanted to really study about manufacturability of the blend. So coming from the literature, so earlier flowability was characterized talking about the flow function, which I discussed in my previous slide. So the flow function concept really came from the sandcastle test, which may also be called uniaxial test, basically. So in this, basically flow function is characterized or defined in terms of ratio of consolidation stress to the unconfined failure strength. Talking in details about this test is basically, you get a mold, you get a powder, and you have two dyes, and then you compact the powder at a high consolidation strength. Then you remove these confined walls and see the failure plane. You know the consolidation strength, and you know the strength at which the powder breaks. So ratio of it will be actually the flow function of the powder. If you talk regarding this test, yes, this test is really useful when the powder has high tendency to get cake. But in most of the powders, if they do not have caking capabilities, or they do not form to have caking strength, so then it's a very difficult, or let's say not reliable test to predict the powder flowability. So moving on to that, so we got basically a Brookfield powder flow tester, which really works on the principle of Janicki methodology. So it's a software controlled equipment which applies the stress uniaxially as well as shears the powder. In this Brookfield powder flow tester, we have composition of 4 different tests, such as flow function test, which tells us about the interaction between the particles. The second is wall friction test, which tells us how the powder is reacted to the walls. And then we have time consolidation test. Suppose the powder is consolidated for a long period of time, how will the powder really behave? What will be the flow function? And the fourth one is variation of bulk density. So the test ranges generally from 2 to 30 minutes. So we can really test the volume of powders in 2 different ways. For example, in a standard cell, it requires 263 cc, whereas in a small cell, it requires 30 cc. So there are many features of using a shear tester such as powder flow tester. However, there are some limitations to it. For example, at an early stage of formulation, we do not have enough quantity of the material in terms of talking about pharmaceutical industries. And if the powder wants to be saved in quantity by food industry, yes, then again, quantity is a big issue. Obviously, the powder needs to have a final particle size distribution to test it in the shear tester. And if you see at a formulation stage, so blends are not often in final particle size distribution. Therefore, we really need to find a way to predict the powder flowability using a small quantity of the material. For if we have around 30 cc or more than that, I think shear tester can be used, powder flow tester can be used to predict the powder, to investigate the powder flowability. Yes, however, in the market, we still have one equipment called spin tester, which measures the flow function of the powder using a small quantity of the material. There are limitations to this equipment. Again, it needs to have a final particle size distribution in quantity. Sampling, the way we sample really plays an important role. It is really dependent upon the user. Flowability data is very much dependent on centrifugal forces, because the basic principle of running this equipment is based on centrifugal force. And if we talk about the repeats, we have seen there is a deviation of about 12% in the results. So basically, we really need to develop a new method which determines the flow properties at an early stage using a small quantity of the material. So what we tried was that we tried using basic particle properties, which is forces of adhesion, and then we are trying to investigate about the bond number and trying to relate with the powder flowability. Since we are talking about particle properties also here, we cannot ignore surface energy. So we infer the surface energy of the substance. So we have found that surface energy really does not change with the particle size. So yes, there can be some way to link surface energy with the flowability of the powders in order to link particle properties with the bulk flow properties. So we have developed a model which predicts powder flowability at any chosen particle size distribution, whether it is for a single substrate or for the blend. These were some of the key novel outputs for the VFL project as well. So before jumping onto the technique, I would really focus on the concept of bond number. We can find a lot of literature available in the bond number, which relates powder flowability and the bond number with each other. However, we do not have any equipment which measures the bond number. So I'm going to talk about that. So basically, if we talk about the definition of bond number, it is the ratio of forces of adhesion to the gravity forces. So basically, this technique which I'm talking about, it is measuring the detachment force. From there, we are inferring the surface energy, which has been well validated using IGC also. So from there, we can really get the flowability of any material with any chosen particle size distribution. Since I'm talking about adhesion, so I would really talk about that. What does adhesion forces really mean? So for an example, we have a powder. So there can be different forces acting on it in terms of particle interaction, which is if the powder is too cohesive, then yes, van der Waals forces are really dominant as compared to other forces. But if the powder is not too cohesive, so there are different forces such as van der Waals forces, electrostatic forces, and capillary forces. So these models I have taken from the literature, and the sum of these forces are actually called the total adhesion force, which is really required to separate the particle from its surface. So why adhesion is really important for the food flavorings, or let's say for the food industry? So it basically controls the flavor to minimize the waste and the downtime for cleaning the equipment. And also, for an example, you got a flavor or you got a product with high salt into it, so it's not really good to the customer. So therefore, adhesion is really important to study to control the flavor to minimize the salt or any fat content which is intaken by the customer. So here is a technique which I was talking about. So this is a technique which we have developed to study the detachment forces. The main objective was to link the powder flowability via flow function. So if we talk in details about this technique, first we get the powder. We compact that at a high consolidation strength with a highly polished phase punch. Then we disperse a monolayer of the powder, and when the powder is settled on the substrate, then we cover those so that we do not lose the materials, and then we put it into the sample holder. The sample holder has already got an acceleration data logger, acceleration device, which measures the deceleration at which the particles detach. It is installed into the sample holder. Then we place these all tablets or compacted powder into the sample holder, and then try to study that how many particles are really detached from the substrate. Corresponding to that, we get a level of deceleration, and then we can calculate the forces of adhesion. The work has been modified from Ertan's work, which was again one of the colleagues at Wolfson. So he really studied mainly about flavorings or snap coatings. And since we have modified the technique, now we have got a more modified version, which gives more repeatability in terms of food and pharmaceutical industries. So since I have already explained you the process that we go with compaction, and then we're dispersing a monolayer, and then we place them, we cover them so that we do not lose the material, and then we drop it from a certain height via well-mounted carriage so that we ignore the friction effects, and then we see the detachment behavior, and we can also analyze the particle properties and the shape factor using G3 morphology. So talking about the technique or the in-depth calculation, so we measure the proportion of powder detached at different decelerations. So for the calculation of bond number, we generally see the deceleration at which 50% of the material is detached versus the mass of D50 particles, which indicates the particle force. So these are some of the features of the technique which we have developed. Apart from these features, the beauty of this test is that we get the measure of deceleration level directly because we have got an acceleration device or sensor attached to the sample holder, which measures the deceleration directly rather than going from velocities or image profile cameras. Another advantage is that since we have got 4 compartments in the sample holder, so we can study different flavors at same deceleration or the same drop height. Also, we can use different substrates with the same flavors, like substrate can be different and the dispersion of the powders can be different to study the level of detachment and what are its effect on adhesion. So these are some of the features of this new technique which we have developed. So the equations which are involved in calculation are general basic equations, Newton's second law, that is force is equal to mass into acceleration. We know the mass detached. We know the 50% mass detached at the acceleration. So we multiply mass and acceleration to get the forces of adhesion. And then talking about gravity forces, again, it's m into g. As I already told you, that bond number is defined as the ratio of adhesion to the gravity. So since we know the adhesion and gravity, we can calculate the bond number. We have also developed a model which infers the effective surface energy. So with this, that is why we have named this equipment as mechanical surface energy tester also. So talking about the algorithm. So from forces of adhesion to gravity forces, we go to the bond number. From there, we have developed well-validated empirically, we have developed empirical relationship between the bond number and the flow function of the powder, which is well validated using Brookfield powder flow tester. Another route is that from bond number, we tried to infer the surface energy since our main objective was to link particle properties with the bulk flow properties, because at an early stage, we do not have enough of material with us. So we tried to get a relationship which tells us about the forces of adhesion. And then from there, we can again get to the bond number, and correspondingly to that, we can predict the flow function of the powder. So these were some of the results. So the commonly used powders is acetal is calcium carbonate, and lactose is widely used in food industry. So in this graph, you can see that this is a graph between deceleration and mass detached in terms of percentage. So as you can see, as the powder is more cohesive, you need a high level of detachment of the dispersed particles from the substrate. So you can see the trend clearly. So for the point of calculation, we use 50% mass detached, at which 50% we get the value of deceleration at which 50% mass is detached. Then, since I forgot to tell you in my previous slide that what we did is we compacted the powder with the same substrate and dispersed the same material. However, the other investigation was that if we use different substrates and then disperse the powder onto it, what will be the effect of adhesion? So we use different substrates such as stainless steel, Taiwan, mild steel, and glass. So we disperse lactose material onto the substrate. Surprisingly, we haven't got much deviation. So the deviation was only about 2 or 3%. We have validated these technique using different dispersion material with different substrates, around, I think, around 14 different substrates. And we also tested with food flavorings as well as pharmaceutical powders. And we found that the substrate does not really play an important role as compared to the dispersed material. In other words, dispersion is more dominant as compared to the substrate compaction. I can understand that you will not be, that it's very hard to digest this fact, but we were more surprised. But since we tried it with different materials, so we found this investigation, and in repeatable forms, we found that there is not much deviation, which really tells us that at nano level, if we go, surface energy really is not impacted as compared to the surface texture. That surface texture really plays an important role, which I can really link it in terms of crisps. We have different pressure troughs on the surface texture, and we try to disperse the food flavorings into it. And then we can really see that, yes, there is a level of adhesion. So I think since we are talking about micro scale, we can also use this test to study the level of detachment on food powders. Then talking about the relationship between the adhesion or bond number and powder flowability. So this investigation was done at different consolidation stresses. As we know that the flow function of the powder is, it's a curve which varies with different stresses. We get a point and then we get a curve out of it. So we tested it at different kPas at around 2 kPa and 9 kPa with different 14 materials. And we got a pretty much good relationship which links bond number and flow function. As you can see in the graph, we on the y-axis it's 1 over FFC, not FFC, because 1 over FFC is much more reliable and gives more definite values and more meaning in terms of only the flow function of the powder. So therefore, I did a relationship between 1 over FFC and the bond number. So this relationship was verified with across 60 different powders, not only pharmaceutical, but as well as food powders, different flavorings. Now, it's not, if we talk about flow properties, it's not only talking about flow function, we also need to consider other bulk flow parameters, which is unconfined failure strength, compressibility, and the friction angle. So we did some empirical modeling to study the relationship between all those. So if you can see these materials, there are around 40 different materials which show the pretty good relationship and a good link. And we got such equations, and then we try to link it with the bond number and predict the flowability of the powder. So combining all these relationships, we have incorporated into a toolkit in which we have allowed the user, or we have given an option to the user first, that if you have the Brookfield powder flow tester data, you will get straight away the formulation of the blend by changing the percentage of the mass according to the user requirement. Apart from that, we also incorporated the use of bond number in the toolkit. So basically, we said to the user that you measure the bond number using mechanical surface energy tester, and you feed the consolidation stress as well as particle density. And then the outputs which will be fetched out is unconfined failure strength, bulk density, compressibility, and effective internal friction, as well as the flow function of the powder. So these were the most critical parameters if you talk about bulk flow properties. So yes, we were successfully able to link bond number with the flow function in terms of providing a user an interface, a novel technique, as well as a software toolkit, which can give the flow function prediction using small quantity of the material. So there are two ways in which we can approach or we can use this technique. The simplest approach for the user is that, suppose for an example, you fix the drop height and start testing the materials and see the level of detachment. You get the different detachments at same height. Then you can compare all the powders. Other technique which we recommend is, for example, you have got one material, test a different deceleration at different by making the detachment at different heights. Then you just note the 50% mass. You see the deceleration at which 50% mass is detached, and then use it to calculate the bond number. From there, since I showed you in my previous slide about the relationship between the adhesion and the surface energy, so then we try to infer the surface energy. As I told you, that surface energy is independent of the particle size. So therefore, we can really predict the flow function curve using surface energy and bond number. And then we can, suppose for an example, the user needs to change the formulation, or they have got a different particle size distribution. They can just feed it into the toolkit and they will get the corresponding flow function of the material or the blend. So the unique selling point of this technique is that we can evaluate particle surface forces for the range of different particle materials. Also, since I showed you the results of the difference of effect of dispersion or effect of substrate on the dispersion, so it allows the user to give a blank formulation. You can use a glass and then disperse the material and study the level of adhesion. However, it still stimulates the further research that what will be the role of dispersion or the substrate on the dispersion. Also, it can infer the detachment force. From there, we can calculate the bond number and effective surface energy from just few quantity of the material. At the end of the day, the main objective is to save the cost in industries. So therefore, we have got a technique as well as a toolkit, which really tells you the formulation behavior by saving a lot of pounds, Sorry for the disturbance. So talking about industrial contribution, so we got to produce a method where from a few particles at an early stage of formulation, we can predict the bulk flow parameters. It's a simple method where we study the detachment of the particles. So the contribution is that we avoid different flow issues. We can improve the cost which the industry really takes, or improve the time which really industry takes to develop a new formulation and test it again and again. So what we can do is we can just put the properties of the ingredients and really validate it or predict the flow behavior. And obviously, since the time is saved and the cost is also saved, because these are the two vital parameters in industry to improve the time as well as the cost. So these were some of this is a summary where we have got a novel technique and the method, as well as we were successfully able to link mechanical surface energy as well as bond number with the powder flowability. So these were some of the recent publications which came out of this work. So we have published 2 papers and 2 are under review. So not only about powder flowability, it also helped us in try to link segregation measurements as well, which my other colleague Richard will be explaining you more, talking about segregation as well as linking about industrial case studies. Finally, I would really acknowledge everyone in this slide about the work. Also, I would be thankful to EPSRC for funding the VFL project in terms of supporting the work. Thank you.
Thank you,
Any
Vivek.
questions?
I got actually questions sent to me. Jahinda's asking, have you tried the test without compacting the powders? And if you had a look instead of how much energy hits the walls?
So if you talk about compaction, we just use compaction to form a substrate, not it does not actually involve the include the level of detachment actually, because We also used a polished surface to study the detachment behavior rather than compacting the tablet, because while dispersion, we do not compact the powder.
Young is asking, can you please explain how the adhesion can affect the flavor again?
Okay, for example, I have a crisp, and then I have a salt onto that crisp, and then while packaging, if we do not really know the adhesion behavior, like how the salt will be sticking onto that crisp, and during packaging, the salt gets low and the crisp is on the above, and when it gets to the end product, end consumer, so he will have the crisps without the salt flavorings. So I don't think so he will like it. So yes, adhesion is really important to study that kind of case study, minimum that. So hope that it answers the question.
Okay. I guess so. Yeah, I think Young seems happy. Okay, thank you, Vivek.